Hey there, science fans, let's talk thermometers. The mercury thermometer, a classic, right? But even classics aren't perfect. Mercury thermometers rely on thermal expansion. Heat up mercury, it expands. Simple. But here's the catch. That expansion isn't always perfectly uniform. This means your readings might be slightly off, especially at very high or low temperatures. Plus, mercury has a limited temperature range where it's liquid. Too hot, it boils. Too cold, it freezes. Not very helpful then, is it? So, while mercury thermometers are handy for everyday use, they're not the gold standard for precision temperature measurement. For that, we need to look at other options, like those fancy digital thermometers or even more sophisticated instruments used in labs. Now let's dive into the fascinating world of black bodies. Imagine an object so dark, so absorbent, that it gobbles up all light that hits it. No reflection, no scattering, just pure absorption. That's a black body, and it doesn't stop there. Black bodies are also perfect emitters of radiation. They absorb all wavelengths of light and emit radiation based solely on their temperature. The hotter the black body, the more intense and the shorter the wavelength of the emitted radiation. Now you might be thinking, wait, doesn't everything emit radiation? You're right. But black bodies are special because they emit the maximum amount of radiation possible for their temperature, following a specific distribution of wavelengths we call the black body radiation spectrum. Here's the thing about black bodies, they're theoretical ideals. We can't find a perfectly black object in nature, but we can get pretty darn close. Imagine a hollow object with a tiny hole. Light entering the hole bounces around inside, getting absorbed with each reflection. Very little light escapes back out. This setup mimics the behavior of a black body. Scientists use cavities like this to study black body radiation. By heating the cavity and measuring the radiation coming out of the hole, they can learn a lot about how temperature and radiation are related. It's a clever trick to study a theoretical concept in the real world. Time to talk gases. In a perfect world, all gases would follow the ideal gas law. PV equals nRT. Pressure times volume equals the number of moles times the ideal gas constant times temperature. Elegant. But gases are made up of real particles with real volumes and real attractions between them. At high pressures and low temperatures, these factors mess with the ideal gas law. Think of it like this. Imagine a room full of bouncy balls. At low pressure, few balls. They bounce around with plenty of space. But pack in more balls, high pressure, and suddenly those interactions matter. Real gases deviate from ideal behavior under these crowded conditions. Section 5. Thermometer discrepancies. Why two readings might differ. Ever notice how two thermometers might give slightly different readings, even when measuring the same thing? Frustrating, right? This can be especially confusing when you rely on accurate measurements for important tasks. Well, there are a few reasons for this. Understanding these reasons can help you make better use of your thermometers. First off, no two thermometers are perfectly identical. Even the smallest manufacturing variations can lead to differences. Manufacturing variations can lead to slight differences in calibration or the expansion properties of the materials used. These tiny discrepancies can add up. Second, the way you use the thermometer matters. Are you using it correctly? Are you holding it directly in what you're measuring? Direct contact ensures more accurate readings. Or is it just nearby? Proximity can affect the accuracy. Heat transfer isn't instantaneous, so placement makes a difference. The closer the thermometer, the quicker it can register the temperature. Finally, remember that thermometers themselves have a temperature. This can be a crucial factor. If a thermometer is much hotter or colder than what you're measuring, it can influence the reading. Always let it acclimate to the environment first. It's all about understanding the limitations of your instruments. Knowing these factors can help you get the most accurate readings possible. Section 6. Keeping it constant. Corrections in gas thermometry. Gas thermometers, which rely on the pressure-temperature relationship of a gas, are pretty accurate, but even they need a little help to be their best. One important correction is accounting for the volume of the gas thermometer itself. See, we assume the gas expands into a vacuum, but that's not entirely true. The thermometer's bulb takes up some space. We need to correct for that. Another factor is the gas itself. No gas is perfectly ideal, remember? At very low pressures, gas molecules start sticking to the walls of the thermometer, affecting pressure readings. We need to adjust for this adsorption effect too. Section 7. Finding agreement, how thermometers align at fixed points. To make sure different types of thermometers play nice together, we use fixed points. These are specific temperatures where a substance undergoes a well-defined phase transition, like melting or boiling. The most common fixed points are the ice point, 0 degrees Celsius or 32 degrees Fahrenheit, and the steam point, 100 degrees Celsius or 212 degrees Fahrenheit, of water. By calibrating thermometers at these points, we ensure they agree at these crucial temperatures. Now, what about temperatures between fixed points? We divide the space between them into equal intervals, creating a scale. So whether you're using Celsius, Fahrenheit, or Kelvin, you can be confident that different thermometers are speaking the same language. This method has been used for centuries, from early mercury thermometers to modern digital ones. Scientists rely on this consistency to ensure accurate measurements in experiments and daily life. Whether you're cooking, conducting research, or just checking the weather, calibrated thermometers are essential. Calibration is the key to making sure all thermometers, regardless of type, provide reliable readings. This universal agreement at fixed points ensures that no matter where you are, your thermometer is trustworthy. Section 8. High-altitude cooking pressure, temperature, and boiling point. Ever tried cooking on top of a mountain? It's an interesting experience. You see, atmospheric pressure decreases as you climb higher, and guess what? Pressure affects the boiling point of water. At lower pressure, water boils at a lower temperature. So your pasta might take ages to cook because the water isn't getting hot enough. Frustrating for hungry hikers. To compensate, you can use a pressure cooker. It traps steam, increasing the pressure inside and raising the boiling point. Problem solved. It's all about understanding the relationship between pressure, temperature, and phase changes. Section 9. The glow of heat, blackbody radiation intensity and temperature. Remember how we talked about blackbodies being perfect emitters? Well, the intensity and wavelength of that emitted radiation depend directly on the blackbody's temperature. As the temperature increases, the total amount of energy radiated, the intensity, goes up dramatically. Think about how much brighter a hot stovetop glows compared to a lukewarm one. Not only that, but the peak wavelength of the emitted radiation shifts to shorter wavelengths as the temperature rises. That's why a hot object might glow red, then orange, and eventually white-hot as it gets hotter and hotter. It's all about the connection between temperature, intensity, and the color of light. Section 10. Chilling out. Gas behavior from room temperature to absolute zero. Let's get chilly and imagine cooling a gas down, way down, to absolute zero. 0 Kelvin or minus 273.15 degrees Celsius. As the temperature drops, so does the kinetic energy of the gas molecules. They slow down, moving less and less. At absolute zero, something incredible happens. Well, theoretically at least. The gas molecules would have zero kinetic energy. They would essentially be frozen in place, unable to move or vibrate. Now in reality, reaching absolute zero is impossible, but we can get incredibly close using sophisticated cooling techniques. Studying matter at these ultra-low temperatures helps us understand the fundamental nature of matter and energy. Section 11. Kinetic theory explained, vapor pressure, volume, and molecular motion. Let's dive into the microscopic world of molecules to understand some cool macroscopic phenomena. Kinetic theory helps us explain how the behavior of individual molecules affects the properties of matter in bulk. For example, consider vapor pressure. Imagine a closed container with some liquid inside. The liquid's molecules are constantly moving, some with enough energy to escape into the space above the liquid, forming a vapor. This vapor exerts pressure, and that pressure increases with temperature. Why? Because hotter molecules have more energy, so more of them escape into the vapor phase, increasing the pressure. It's all about the energy of those tiny molecules. Section 12. Heat transfer mechanisms. Conduction in metals and glass. In this section, we will explore how heat moves through different materials, focusing on metals and glass. Ever wonder how heat travels from one place to another? It's a fascinating process that happens all around us. There are three main ways heat can travel: conduction, convection, and radiation. Each method has its own unique characteristics and applications. Let's focus on conduction, which is the transfer of heat through direct contact between materials. This is a common way heat moves in solids. Metals are excellent conductors of heat. But have you ever wondered why metals are so efficient at conducting heat? It's because their atoms are arranged in a tightly packed lattice structure. This structure allows free electrons to move around easily, facilitating the transfer of energy. When you heat up one end of a metal rod, those free electrons gain energy. They then transfer this energy quickly to neighboring atoms, spreading the heat rapidly throughout the metal. Glass, on the other hand, is a poor conductor of heat. But why is that the case? Its atoms are bonded in a more irregular structure, which makes it much harder for heat to transfer efficiently. This irregularity acts as a barrier to the flow of heat. That's why a glass of ice water stays cold longer than a metal cup. The glass acts as an insulator, slowing down the heat transfer from your hand. This insulating property of glass makes it useful in many applications where heat retention is important.